think we can start, and I just mention a few words, and then I leave the scene to Melissa. Okay, so thank you everyone for coming, and both from the physics and the math communities, and also we were very happy last time to have so many of you. So I'm Matteo. I am organizing the seminar series Combinatorics, Physics and Probability at Harvard CMSA, together with Michael Simkin. And so seminars will be every Tuesday from 9:30 to 10:30 US Eastern Time. So if you haven't already done so, please join our mailing list to keep updated with the upcoming talks by registering at the CMSA website, and I will share the link in the chat soon. Someone asked me about videos and recordings. So these seminars will be recorded and we will be soon available on the CMSA website. I will email you when the first video will appear, will be uploaded, and tell you where to find them. The purpose of this seminar is to explore two main threads. One is the intersection between combinatorics and high energy physics, and the second would be about the intersection between combinatorics and probability, which would be more Michael's domain, and you will hear more next week. So I'm happy today to continue exploring combinatorics, also with motivation from physics, with the second talk of the series, given today by Melissa Sherman-Bennett from the University of Michigan, the Departments of Mathematics. And she will talk about the hypersimplex and the m = 2 amplituhedron. We will leave 10 or 5 minutes at the end for questions, but feel free to ask brief questions maybe during the talk, either on the chat or unmuting yourself. And so please, Melissa, feel free to start.
Thank you. Yeah, thanks so much for the opportunity to speak. I will be able to see the chat here, so feel free to put questions in the chat. Yeah, so I'm talking about some joint work with Matteo Parisi and Lauren Williams, and all the details are in a paper on the archive, so check there if you want to see more. Okay, so as Matteo said, I'll be talking about these two objects, the hypersimplex, which I think of as an object of a lot of interest to combinatorialists, probably also of interest to others, and the m = 2 amplituhedron of interest to physicists, particularly people who think about scattering amplitudes. Before I talk about these two objects and their, to me, still fairly mysterious connection, I need to talk about a third object, which is going to be lurking in the background. So this is just to help me define some things. Okay, so this object is a subset of the Grassmannian. So first, let me just fix some notation about the Grassmannian. I'm going to pick two positive integers, k less than n, and then I have some kind of standard notation for the interval of integers from 1 to n, and all k element subsets of 1 through n. Okay, so this is a real Grassmannian talk, not a complex one. So for me, grkn denotes the subspaces of r to the n of dimension k. Okay, and I think about the Grassmannian, I think exactly the same way as everyone else, so there's going to be no surprises here. So if you pick some element of the Grassmannian that is a k-dimensional subspace, then you can choose a representative matrix for that subspace. And that representative matrix, it should be full rank and k by n, and its row span should be exactly the subspace V. Okay, and I think about these matrices, these representative matrices, so that I can talk about some coordinates on the Grassmannian called Plücker coordinates. These are indexed by k element subsets of 1 through n. So pick one of those, call it I. The Plücker coordinate piece of I is just the maximal minor of the representative matrix A, which is located in column set I. So I'm taking the kind of largest submatrix in column set I, and I'm just taking its determinant, and that's the Plücker coordinate. Okay, and these are projective coordinates, so they're defined up to common rescaling. Okay, so I'm going to care particularly about a particular subset of the Grassmannian called the totally non-negative Grassmannian, or TNN Grassmannian for short. So this was defined independently by Lustig and Postnikov in very different language. It's kind of not at all obvious that they were actually defining the same thing, but they were. This is the one I'm going to tell you is Postnikov's definition, in case you're interested. So the totally non-negative Grassmannian is just all of those elements of the Grassmannian whose Plücker coordinates are non-negative for all I. So kind of what you think it ought to be from the name. And the totally non-negative Grassmannian, it turns out to be a very beautiful space. There's a lot of really interesting combinatorics going on here. Someone could easily give a talk just about the totally non-negative Grassmannian. I'm not going to do that, but one thing I will say about it is it turns out, so it has a very natural stratification And that stratification ends up being very nice topologically. So what is the stratification? Well, what you do is you just, in each stratum, you collect all of the points of the totally non-negative Grassmannian with the same +/0 pattern of Pluker coordinates. So a little bit more formally, or to give some notation to that, so choose some collection of k element subsets of n, so call that collection M. The stratum indexed by M, S sub M, is all of those elements of the totally non-negative Grassmannian where P sub I is positive precisely when I is in my collection M. So M is telling me which Pluker coordinates are positive, and then all of the other Pluker coordinates ought to be 0. Okay, so here's an example of one of these stratum. So if I consider the subspaces with representative matrices that look like this, where A, B, and C are all positive real numbers. Okay, so if I look at this matrix, I can compute its Pluker coordinates and they will all be non-negative. In fact, they'll all be positive except for one of them, which is P12, because these two columns are parallel. And yeah, in fact, this describes all subspaces with that 0 non-zero pattern of Pluker coordinates, or +0 pattern of Pluker coordinates. So this is the stratum indexed by the collection, all 2 element subsets of 4, except for the subset 1, 2. Okay, so of course, if you choose your collection of subsets badly, then your stratum SM might be empty. So we don't care about those. We only care about the non-empty ones. And if your stratum is not empty, then you call M, the collection of subsets, a positroid of type Kn. So the word positroid is a portmanteau of positive and matroid, or positively realizable and matroid. And then this type Kn part is just telling us that the Grassmannian we're thinking about is GRKn. And then we call the stratum a positroid cell. And the word cell here is not an accident. In fact, this stratum, it really is homomorphic to an open ball. Okay, so kind of by definition, the totally non-negative Grassmannian is the disjoint union over positroids of type Kn of SM, this positroid cell. And it turns out this decomposition is sort of exceptionally nice. It won't matter for the purposes of this talk, but it's a regular CW complex. That's a result of Gaussian carbon lamb. Okay, so now that I've talked about this object that wasn't in my title, the totally non-negative Grassmannian, let me move on to the 2 objects which are in my title, so the hypersimplex and the amplituhedron. So both of these objects are images of the totally non-negative Grassmannian under a particular map. So the maps are different on the 2 sides. On the hypersimplex side, we'll be looking at the moment map. And on the amplituhedron side, we'll be looking at the M=2 amplituhedron map. Okay, so let me start here on the hypersimplex side. So, and with the moment map. So the moment map is a map from actually the whole Grassmannian to Rn. It has this particular form. It won't matter too much exactly what the moment map, how the moment map is defined for this talk, so I'm not going to really say anything about this formula. From the perspective of combinatorics, the moment map is maybe particularly significant because of some work, classical work of Gelfand, Goretzky, McPherson, Serganova. So they were thinking about moment map images of torus orbit closures in the Grassmannian. And it turns out that those moment map images of torus orbit closures, so they sit in Rn, they're actually polytopes, they're actually matroid polytopes, if you're a person who knows what that means. So there are some pretty nice polytopes. We are going to be thinking about the moment map image of the totally non-negative Grassmannian. And okay, so, and what that is this object called the hypersimplex. So delta k plus 1n is the moment map image of the TNN Grassmannian k plus 1n. And okay, I'll give you a caveat here. This is like the least friendly way to define the hypersimplex ever, I think. So I will give you a more friendly definition in a second. I want to define it this way for the sake of an analogy. Okay, and so for now, what will I say about the hypersimplex? Well, it's a polytope sitting inside of Rn. It's actually it contained inside of a hyperplane. So but it's full dimensional inside of that hyperplane. So it's n-1 dimensional. Okay, so that's the hypersimplex side. It's just some polytope defined using the moment map. So now let me talk about the amplituhedron side. So the amplituhedron was defined by two physicists, Arkani-Hamed and Trnka. And so they were interested in coming up with some geometric object which encapsulated scattering amplitudes. I'm not a physicist, so I'm not going to say really anything about scattering amplitudes except for this. So scattering amplitudes are functions whose input is data about particles moving around, and whose output is the probability that those particles will kind of smash together and scatter into new particles. And Arkani-Hamed and Trnka wanted a geometric object which would kind of help them compute scattering amplitudes. The very, very rough and mathematically imprecise thing to say is that they're looking for an object whose volume is a scattering amplitude. Okay, so what they came up with was the m equals 4. Well, what they came up with was the amplituhedron. We'll talk about the m equals 2, 1, not the like general m1. So to define the m equals 2 amplituhedron, you need to pick first a matrix Z. So this is going to be n by k plus 2. And it should have positive maximal minors. Okay, so now that you have this matrix, you are going to use it to define a map from the totally non-negative Grassmannian for Kn to a different Grassmannian, grk k plus 2. And okay, so this map, I'll denote it by Z tilde, and it's just the map induced by matrix multiplication by Z. So if you have some element of the TNN Grassmannian, it's represented by a matrix A, then the Z tilde map sends it to the subspace represented by the matrix A times Z. And that subspace will be a k-dimensional subspace and in a k plus 2 dimensional vector space. So it's inside of grk k plus 2. Okay, you might be a little bit worried, like what if A times Z doesn't have full rank, then that matrix won't represent an element of this Grassmannian, but not to worry. The assumptions we're making about the domain and Z will ensure that A times Z does have full rank. Okay, so that's the amplituhedron map, this Z tilde induced by matrix multiplication. And the m equals 2 amplituhedron is just the Z tilde image of the totally non-negative Grassmannian. Okay, so what am I going to say about this? Well, the hedron part of amplituhedron is kind of aspirational. It is not usually a polytope. The other thing to say about it is that it's full dimensional inside of its ambient Grassmannian, so it's 2k dimensional. So for the hypersimplex, I was like, oh, this is a very unfriendly way to define the hypersimplex. I'll give you a much nicer definition in a second. For the amplituhedron, one of our results is a nicer description of the amplituhedron, which was originally conjectured by Arkani-Hamed, Thomas, and Trnka. I'll talk about that later. But before our results, kind of this was the only way we knew to define the amplituhedron. Okay, so those are the two big objects, the hypersimplex and the m equals 2 amplituhedron. But remember, so we've got these totally non-negative Grassmannians on both sides. And in the previous slide, I told you both of these TNN Grassmannians decompose into a disjoint union of positroid cells. So we can also think about the images of these positroid cells under the two maps. Okay, that's what I'm going to define next. So on the hypersimplex side, if I take the moment map image of a positroid cell closure, I get something called the positroid polytope, gamma m. So this is some polytope. It's sitting inside of the hypersimplex in some way. I'll give you a nicer description of it again in a little bit. So that's the hypersimplex side. You get these positroid polytopes. On the amplituhedron side, if you take the Z tilde or amplituhedron map image of a positroid cell closure, you get what I'm going to call a grasstope. I'm going to denote that by Zn. So grasstope is a portmanteau of Grassmann polytope, which is the terminology that Thomas Lamb came up with. Again, this is not a polytope, it's something else usually. Okay, and there's a question in the chat. The closure is with respect to the Euclidean topology. Yeah. Okay. It may actually coincide with the Zariski topology. I can't quite remember in this case. Okay, so from the combinatorial perspective, kind of no positroid polytope is really like that much more interesting than another, or maybe like a better way to say it is all positroid polytopes are like kind of worthy of study. And they're kind of on equal footing. But from the physics perspective, actually some grasstopes are kind of hard to handle. And so we're going to focus on the ones that are kind of the easiest to handle and maybe the most important for the main question about the amplituhedron, which is this problem of computing its volume. Okay, so basically, these positroid cells, because they're very nice objects, their volume, right? It's not actually their volume, it's something else. It's like a canonical volume form is known. And so if you want to understand the volume of the amplituhedron, the grasstopes you should look at are the ones that are sort of as close as possible to positroid cells. So what I mean by this is they should be the grasstopes where Z tilde did not squish the positroid cell at all. So Z tilde was injective on the positroid. And also because we care about sort of computing the volume of the amplituhedron, we want to focus on grasstopes which are full dimensional. The lower dimensional ones won't help us in any kind of volume computation. So we're going to pay special attention to grasstopes which are called positroid tiles. So these are exactly the thing I said before. So it's full dimensional grasstopes. So that's 2K dimensional grasstopes, where the Z tilde map was injective on the positroid cell Sn that the grasstope is the image of. Okay, and kind of looking at this definition, you can make an exactly analogous definition on the hypersimplex side at this moment, and kind of for for no reason at all, but just because you can, but you'll see why. So on the hypersimplex side, we can also define a positroid tile, so these will be the full dimensional, i.e. n-1 dimensional positroid polytopes, where the moment map mu is injective on the positroid cell Sn. Okay. And now the next kind of construction of interest to us will be positroid tilings. So these are again motivated by the amplituhedron side. These are exactly the decompositions of the amplituhedron that you would look at if you wanted to compute its volume, right? So let me tell you what they are first. So a positroid tiling of the amplituhedron is a decomposition of the amplituhedron into positroid tiles with disjoint interiors. Right, so why is this the object? Why is this the kind of decomposition we're looking at? Well, the tiles are exactly the grasstopes whose volumes we can compute easily. And so to compute the volume of the amplituhedron, we want to decompose it exactly into these pieces whose volumes we know, and we want to decompose it in a way so that their interiors don't overlap, right? If we want to, we want the volume of this thing to just be the sum of the volume of all of these pieces. Okay, so again, we can make an exactly analogous definition on the hypersimplex side and look at kind of analogous decompositions of the hypersimplex. So on the hypersimplex side, a positroid tiling is a decomposition of the hypersimplex into these tiles, positroid tiles with disjoint interiors. Okay, so like I said, on the physics side, this is really a problem motivated by physics and this problem of computing scattering amplitudes. On the combinatorial side, if you look at this, it might look a bit funny. It's not like clear that positroid tilings are sort of a good kind of decomposition to look at from a combinatorial perspective. One thing that I'll point out here is in this tiling definition, I'm not making any assumptions about how the boundaries of the tiles interact. So this is a substantially weaker notion than like a a subdivision, a polyhedral subdivision into positroid polytopes. But on the other hand, a special case of a positroid tiling is a subdivision of the hypersimplex into positroid polytopes, where all of the largest positroid polytopes in that subdivision are exactly some of these positroid tiles. So those sorts of decompositions of the hypersimplex into that kind of positroid polytope, those are a fairly natural thing to study from a combinatorial perspective. So you should think of these positroid tilings as just a bit more general than something that's like quite natural. So maybe they're not too bad in and of themselves. Okay, so why have I spent such a long time defining all of these things right next to each other? Well, what I'll be talking about for the rest of the talk is this curious parallel. So in fact, we'll have some bijections operating on levels 2 and 3. Before I go into that, let me just give you a kind of better idea of the objects floating around on both sides. So first, the hypersimplex and positroid polytopes. I promised a friendlier definition of both of these objects, so let me give that to you now. So some notation, if I is a subset of 1 through n, E sub I is going to be the indicator vector of that subset sitting in Rn. So it's a 0, 1 vector with 1s in precisely the positions indexed by I. Okay, so the hypersimplex delta k plus 1n is just the convex hull of all indicator vectors of k plus 1 element subsets of n. So its vertices are exactly the 0, 1 vectors with exactly k plus 1 ones. Here's an example for delta 2, 4. So as you can see, its vertices are indexed by 2 element subsets of 4. Okay, so that's the hypersimplex. To get a positroid polytope gamma m, all you do is you look at the hypersimplex and you just throw away those vertices which don't correspond to subsets of m, or subsets in m. So, so the positroid polytope gamma m is the convex hull of all the indicator vectors of the subsets I, which are in your collection M. So here's an example of a positroid polytope. And it's the positroid polytope of the positroid I mentioned as an example on the first slide, where all of the 2 element subsets of 4 are in the positroid, except for 1, 2, that's not in the positroid. So this positroid polytope is the moment map image of this positroid cell. Okay, this is just to remind people in the audience that these positroid polytopes, even among matroid polytopes, they're special. So if, for example, this thing over here is a matroid polytope, if you're familiar with what that is, but it's not a positroid polytope. Okay, so we have these nice descriptions of the hypersimplex and positroid polytopes just as subsets of Rn. We don't have to talk about this totally non-negative Grassmannian in the background. And we also have a full characterization of the positroid tiles. So these were the kind of the positroid polytopes we were going to care about especially. So this characterization is due to Lukowski, Parisi, and Williams. They gave it in a bit of a different form. I'm combining their characterization with the result of Spire and Williams to phrase it like this. So the positroid tiles for the hypersimplex, they're just the smallest full dimensional positroid polytopes. So they're exactly those full dimensional positroid polytopes which don't properly contain another one. So that's kind of nice, right? So the positroid polytopes we care about in particular, they're like the smallest pieces that we're going to see if you're thinking about positroid polytopes as a whole. Okay, and another quite nice thing about the hypersimplex side is we have a good combinatorial source for many positroid tilings. This combinatorial source is called the Positroid. This is I'm not going to define it, but I'll just tell you it's a complete polyhedral fan in some vector space. It was studied pretty recently independently by Arkani-Hamed, Lamb, and Spradlin, and separately by Spire and Williams. And the Positroid, it's an object which parametrizes regular positroidal subdivisions of the hypersimplex, but in particular, the points in its maximal cones, right? So it's a fan. So the points in its maximal cones, they'll give you a positroid tiling. In particular, they'll give you a positroid tiling where boundaries are interacting nicely. So they're actually giving you a positroidal subdivision, but they also give you positroid tilings. Okay, I just got a little thing saying my internet connection is unstable, so I hope that was not lost to the ether. Okay, so the takeaway from this slide is basically on the hypersimplex side, we have a pretty good understanding of a lot of what's going on. And we have this nice kind of global object telling us about the structure of well-behaved positroid tilings. On the Amplituhedron side, I can tell you much less. So this is just to remind you what the definition of the Amplituhedron is. And before our results, you could really only give a nice description of the Amplituhedron for two parameter values. So one of these parameter values is for k equals 2, when k plus 2 equals n. So in this situation, so the Z matrix you picked was n by k plus 2. So in this situation, your Z matrix is square. That means that your Z tilde map is actually an isomorphism. So the Amplituhedron is just isomorphic to the totally non-negative Grassmannian in that case. And here there's only one positroid tile. So the positroid tilings just consist of like one tile. They're not very interesting. The other parameter value where we know what's going on is for k equals 1. So in that case, the Amplituhedron is actually a polytope. It's a polygon sitting in the projective plane, and it has n vertices. So it looks something like this for n equals 6. So, and it turns out the vertices of this polygon, which is the Amplituhedron, they'll be given by the rows of the Z matrix. And those rows, so those vectors, they'll be arranged clockwise in the projective plane. So in this situation, the positroid tiles are actually just triangles sitting inside of this polygon. So the positroid tilings are just usual triangulations of a polygon. Okay, and for all other k, I can't give you, or before our results, I couldn't give you any other description of the Amplituhedron besides this one. And the only thing I could say about the tilings are that some results of Bao and He give you a recursion to produce tilings of the Amplituhedron, but we don't have like some nice mathematical object floating in the background, which is parametrizing any sorts of tilings, or we don't know about such an object. Okay, so that's the state of affairs before our results. So now let me tell you what our results are. So the motivation for this is some conjectures of Lukowski, Parisi, and Williams. So based on some numerical coincidences, they defined a map called T-duality, which is a map on the level of positroids. So T-duality takes certain positroids of type k plus 1n, and it sends them to another positroid. So if your original positroid is m, let's call the T-dual positroid m hat, and this positroid is going to be type kn. Okay, so this is a level. So this is a map which is matching up positroids of two different types. And so that means it's also matching up positroid cells sitting inside of two totally non-negative Grasmannians. So so T-duality matches up a cell SM sitting inside of TNN or K plus 1n with another positroid cell SM hat sitting inside of a different TNN Grassmannian. Okay, and it also matches up a positroid polytope, the one indexed by m, so gamma m sitting inside of Rn. It matches this up with a grasstope Zm hat, which is sitting inside of the Amplituhedron ANK2C. Okay, so what is the point of this T-duality? Well, somehow it seemed to be matching up precisely those positroid polytopes and grasstopes on which the moment map and the Amplituhedron map were particularly well behaved. So their first part, they made kind of two conjectures. In the first part is that the T-duality, this matching up of m and m hat, it's actually matching up the positroid tiles for the two sides. So they conjectured that the positroid polytope gamma m is a positroid tile for the hypersimplex, if and only if the T-dual Grasstope Zm hat is a positroid tile for the amplituhedron. And then the second part of their conjecture is that, moreover, this T-duality, this way of pairing up positroid polytopes and Grasstopes, it actually induces a bijection between the positroid tilings of the two spaces as well. So a collection of positroid polytopes is a positroid tiling of the hypersimplex, if and only if, when you take a collection of T-dual Grasstopes to all those positroid polytopes, you get a positroid tiling of the amplituhedron. Okay, so before I go on, let me just say a little bit about why this would be an attractive result, or kind of like why would you want to prove something like this? So one reason you'd want to prove something like this is just that it's really weird. So this is like something that they're conjecturing based on numerics matching up, but the amplituhedron and the hypersimplex are two very different spaces. You know, the moment map and the amplituhedron map are quite different. So this is just sort of, yeah, it's kind of, it would be really, it's just very interesting if it were true, because the spaces seem so different. The other reason why it would be nice to prove something like this is because, well, I hope I convinced you a couple of slides ago, we have a lot of understanding of what's going on the hypersimplex side. Things that are really nice there, everything is convex. We have the tools of convex geometry. There's a lot of nice combinatorics. On the other hand, on the amplituhedron side, it's much more difficult to figure out what's going on. Things are not convex, they're curvy, they're sitting inside of a Grassmannian, not a vector space. Yeah, so it's also nice to be able to take things from this side. We have all these positroid tilings of the hypersimplex we already know about from the positive Dressian. It would be very nice to kind of port them over to this other side and get a bunch of positroid tilings for the amplituhedron. Okay, so that said, the result I'm going to tell you about today is that both of these conjectures are true. So on the level of tiles, we show that that T-duality gives a bijection between positroid tiles on the two sides. We also do something a little bit more. So these positroid tiles, these Grasstopes, the only description we had for them in the beginning is just that they're the amplituhedron map images of certain positroid cell closures. And what we do is we'll actually give inequality descriptions of these tiles, Zm hat, just as subsets of GRKK plus 2. So we'll say, okay, the tile is those elements of GRKK plus 2 satisfying certain inequalities. So we give an intrinsic description of the tiles without referencing this TNN Grassmannian sitting in the background. And the nice thing is that the inequality description we give of the Grasstope tiles, Zm hat, they exactly parallel the inequality description of the T-dual Grasstopes, gamma M. So, right, or sorry, T-dual positroid polytopes. Right, so polytopes just have inequality descriptions. They're cut out by hyperplanes. So, yeah, it's a, so the, I'll tell you what these descriptions are. The inequalities aren't literally the same, but you need kind of exactly the same data to give the inequalities for tiles on both sides. Okay, so that's on the level of tiles what we do. And you can imagine having a good description of the tiles Zm hat sitting inside of GRKK plus 2. It helps you do lots of things. So we prove a couple of conjectures and do a little bit more. And then on the level of tilings, we show this, that T-duality induces a bijection between positroid tilings of the two spaces as well. Okay, so before I tell you a little bit more about both of these results, I'm going to pause briefly for questions. Okay, I'm going to take that as a sign that there are no questions, so I'm going to press ahead. Okay, so so let me tell you about a bit about our positroid tile results. So, okay, so someone asked, the inequality description is using Fluker coordinates. Okay, and so the answer to that is no. I'm actually going to use some other functions on the Grassmannian called twistor coordinates. These are linear functions in Fluker coordinates. So yeah, it's not, so you can write them down in terms of Fluker coordinates, but those are not the inequalities that we'll be dealing with, just like Fluker coordinate is something or other. Yeah, I'll tell you what the twistor coordinates are in a second. Okay, so for the positroid tiles, so we show that they're in bijection, so that T-duality gives this bijection. Another thing that we do is, and kind of maybe the better way to think about it, is we show that positroid tiles on the two sides are both in bijection with some combinatorial object, which is going to contain all of the information about the tile. And that combinatorial object is a properly bicolored subdivision of an n-gon with area K. So it's a picture that looks like this. So a subdivision of an n-gon means, well, I've split my n-gon into smaller polygons using diagonals of the n-gon. The bicolored part means I've colored each smaller polygon either black or white, and the properly bicolored means that if I have two smaller polygons which share an edge, they'll be different colors. So I couldn't have this polygon be black. The area K part, that's just keeping track of how much of the large polygon is covered by black polygons. So to compute it, what you do, you just triangulate each black polygon and count the number of black triangles. So here, to triangulate the black polygons that I see, I need to add another arc. Once I do that, I see 3 black triangles, so this thing has area 3. Okay, so given a picture like this, one thing I could do is I could actually tell you what M and M hat are. I won't give you that recipe right now for the sake of time, but it's a very straightforward combinatorial recipe to get either M or M hat from a picture like this. And the other thing you can do is you can actually read off the inequalities, cutting out both of these tiles out of their ambient spaces. So for the amplituhedron side, like I mentioned, I'm going to need to define some new functions, some twistor coordinates, and those will be the functions appearing in my inequalities. So let me do that quickly. So pick some y in grkk plus 2 and let zi denote the ith row of z. So the twistor coordinate, to define the twistor coordinate, I need to pick 2 numbers ij between 1 and n. And then the twistor coordinate yij is just the determinant of the matrix where I put y in the top, and then I put the ith row of z and then the jth row of z. And y has k rows and k plus 2 columns. So this matrix here is square, so I can just take its determinant, that's fine. So that's what the twistor coordinates are. I'll say these coordinates don't come out of nowhere. They appear frequently in the physics literature. Maybe one place they show up is in a conjecture of Arkani-Hamed, Thomas, and Trnka on a description of the amplituhedron just as a subset of grkk plus 2, without mention of this totally non-negative Grassmannian in the background. I'm just going to flash this on the screen. I'll talk a little bit more about it later. Okay, so someone hands you a properly bicolored subdivision of a polygon with area K, and you would like to produce the positroid tile for the amplituhedron that it corresponds to, so some zm hat. So what you do, okay, so first you're going to triangulate all the black polygons of your subdivision. So you end up with some picture that looks like this. And then you're going to write down some inequalities. There will be one inequality for each arc of a black triangle. So for example, one of these arcs is the arc that goes from 1 to 4. So that will give me one inequality. And the inequality will tell me the sign of the twistor coordinate y14. My inequality will look like -1 times y14 to the something, or sorry, -1 to the something times y14 is positive. Okay, so what's this something here? Well, it's this combinatorial statistic, again, denoted using area, so it's area I to j. So all this is, area I to j, is the number of black triangles to the left of the arc I to j. So in this situation, to compute the exponent, all I do is I look at the arc 1 to 4, and I count how many black triangles are to its left. I only see 1. So that means my exponent on the -1 here is 1. And so the twistor coordinate y14 will be negative on this tile. Then if I wanted to pick another one, maybe y46. So this arc will tell me the sign of the twistor coordinate y46 on my tile. So the exponent here is the number of black arcs, black triangles to the left of my arc. I see none of them. So the exponent is 0 and y46 will be positive on my tile. Oh, and I should mention I is less than j here. Okay, and so that's it. That is the inequality description of the tile, is you just take all of these inequalities on signs of twistor coordinates given by the black arcs of this triangle. Right. And so as I mentioned, you can use exactly the same data, this area statistic, to give the inequality description of the T-dual positroid polytope, which is a tile for the hypersimplex. So the inequality itself will be different, of course. So I'm not talking about twistor coordinates now in the inequalities. Instead, I'm talking about sums of consecutive coordinates of some vector in Rn. But the bounds on these sums are still given by the area statistic. Okay, so that's how you get the tiles on the two sides. Just you read them in this really straightforward way off of these subdivisions. And like I said, now that we have kind of this very, very concrete description of the tiles on the Amplituhedron side, you can kind of do some more stuff. So one thing that we do is we prove this conjecture of Arkani-Hamed, Thomas, and Trnka on the intrinsic description of the Amplituhedron as a whole. Oops, my pen is something on. Okay, so I'm not going to say too much about this, but what this intrinsic description is the Amplituhedron is the closure of those elements of the Grassmannian GRK+2, where n twistor coordinates are positive, and a particular sequence of twistor coordinates has precisely k sign changes. So that is what the Amplituhedron is. Oh, I should also say one inclusion. This inclusion was proved independently by Arkani-Hamed, Thomas, and Trnka, and Karpin-Williams. So what we do is we prove the opposite inclusion. Okay, so another thing that we do, which I'm not going to say really very much about at all. I'm just going to say it in case there's someone in the audience who's interested in cluster varieties or cluster algebras. Another thing we do is we find new cluster varieties in GRK+2. We find one for each positroid tile. And so these cluster varieties are also in bijection with these properly bicolored subdivisions with a certain area. So these cluster varieties are really nice. They're type A1 or like A something times A something times et cetera times A something. Their cluster variables are not Pluker coordinates, but they're signed ratios of twistor coordinates. And the positive parts of these cluster varieties are exactly the positroid tiles. Okay, and if you're interested in hearing more about this, stick around afterwards and ask me some questions. I'm not going to say anything else about it now. Okay, so now let me move on to tilings for the last little part of the talk. So this is just to remind you what the tilings are. So tiling on either side is some collection of tiles whose union is the whole space and whose interiors are disjoint. And this is, yeah, again, just to remind you, on the hypersimplex side, we have a good source for tilings. They come from the maximal cones of the positive Dressian. And on the Amplituhedron side, the only global understanding we have of positroid tilings is at the k=1 level. So by global, I mean like non-recursive. At the k=1 level, we're just looking at triangulations of a polygon. For other k, kind of who knows. Okay, so our results along in this direction is, again, this bijection between positroid tilings of the hypersimplex and positroid tilings of the amplituhedron, which are positroid tilings no matter what z you pick. So remember, we had to pick some z in the beginning to define the amplituhedron. So you could wonder, well, maybe you have some positroid tilings that are, well, some collection of grass topes, which forms a positroid tiling for some z, but not for all of them. So the ones that we're picking up here in this bijection are exactly the positroid tilings that kind of persist for all z. So they're positroid tiling no matter what z you pick. Okay, and here's a little picture of this bijection in the only situation that I can draw. So the hypersimplex is delta 2,4 and the amplituhedron is A412. So delta 2,4 has two positroid tilings. Here they are. And so focusing on this one, so one of the tiles in this tiling is this blue positroid polytope. Its T-dual grass tope is this blue positroid tile over here. And then similarly for the green ones. And so you can see if I take both the blue and the green tile and I take their T-dual grass topes on the other side, I do indeed get a positroid tiling of the amplituhedron and vice versa. Okay, so how do we prove something like this? Well, what we do is on both sides, we're going to take the simultaneous refinement of all positroid tilings. So this breaks up the hypersimplex and the amplituhedron into even smaller pieces than the tiles, right? Breaks it up into pieces that fit inside of all tiles. And then we look at this. So we look at this decomposition into even smaller pieces, and we look at the pieces and we try to match up the pieces on the two sides. We kind of hope that that works out. And it more or less does, and that's how we prove this theorem. So to give you just a little bit more detail, if you take the simultaneous refinement of all positroid tilings on the hypersimplex side, you get something classical. So what you get is, in fact, a triangulation of the hypersimplex, so a decomposition into simplices, due originally to Stanley, though it was later studied in kind of different guises by Sturmfeld and then Lamb and Postnikov. Okay, so for us, the important thing about this triangulation is that the maximal simplices, so the largest pieces of this triangulation, they're indexed by permutations of n-1 with k descents. So I'm going to denote those maximal simplices by delta w, we call them w simplices. W is one of those permutations of n-1 with k descents. And so yeah, there are Eulerian-number-many of these maximal simplices. Okay, so just to remind you, this is what you get when you do take the simultaneous refinement of all tilings. This decomposition. Okay, on the hypersimplex side, what happens when you take the simultaneous refinement of all tilings? Well, remember our tiles are given by these sign conditions on twistor coordinates, right? So you're in the tile if some particular collection of twistor coordinates have particular signs given by this subdivision, or given by this subdivision of a polygon. So if you're taking the simultaneous refinement of all tilings, that means that you're specifying the signs of all twistor coordinates. So what we do is we define sign chambers of the amplituhedron. So you pick some sign vector epsilon, and the sign chamber delta hat epsilon, this is going to be all those elements of the amplituhedron where the twistor coordinates have the sign specified by your sign vector epsilon, and then you should take the closure. Okay, so by definition, the amplituhedron is the union of all of these sign chambers, but many sign chambers will be empty. And this is because these twistor coordinates whose signs we're specifying to define the sign chambers, they're very far from algebraically independent. So they satisfy like 3-term Plukha relations basically among them. So you can't just like freely choose the signs of each twistor coordinates alone. Some combinations aren't possible. And so this is good, right? Because there are many more sign vectors than there are permutations of n-1 with k descents. So if we didn't have a lot of sign chambers being empty, we definitely would not be able to match up the pieces of these simultaneous refinements. Okay, so the problem here is to really figure out which sign chambers are non-empty in the amplituhedron. So basically what we do is we make a guess for the non-empty ones and then show that in fact that is all of the non-empty ones. So our guess, we call them W chambers. So, and they're naturally in bijection with the W simplices. So for each W simplex, I'm going to define a W chamber, which is a sign chamber in the amplituhedron. And it's not too important, I guess, exactly how it's defined. The sign of a the twistor coordinate is specified in some way by some statistic on the permutation W. Yeah, okay, so you can define it in some way. Here's a little schematic. On the one hand, here is a W chamber, a W simplex in the hypersimplex, this green thing. And then the T-dual W chamber is this little green triangle in the amplituhedron. Okay, and the hope, so W chambers are in bijection with W simplices. So the hope is that as we vary W over all permutations of n-1 with k descents, the W chambers actually cover the amplituhedron. And this is true. So the amplituhedron is the union of all of the W chambers. So we have a decomposition of the amplituhedron where the pieces match up with the pieces in this decomposition of the hypersimplex. And even better, kind of the pieces behave the right way with respect to inclusion into tiles. So what I mean is, if you have some W chamber and an amplituhedron positroid tile, and the W chamber is non-empty, the W chamber is included in the positroid tile for the amplituhedron if and only if the T-dual W simplex is contained in the T-dual positroid polytope. So yeah, T-duality is kind of doing the correct thing with respect to inclusion for these W chambers and W simplices in the positroid tiles. Okay, so if you look at a result like this, you might think, oh, well, that's it, right? That basically should give you the result about tilings being in bijection. The issue is actually, so it doesn't. The issue is this assumption. So it is possible that for some values, my internet connection may be unstable again. So it's possible that for some values of Z, some choices of Z, W chamber is empty. And then for some other values, maybe it's not empty. So to prove the bijection between tilings, you have to somehow get around this issue. Okay, so quickly, let me just explain the phenomenon of these W chambers sometimes being empty. So let's think about the k=1 situation. In this situation, the amplituhedron is just a polygon. And the hypersurfaces where the twistor coordinates vanish, those will just be lines between vertices of this polygon. So in order to describe a W chamber or a sign chamber of the amplituhedron, you just need to tell me which side of like each line between two vertices I should be on. Okay, so one example of a sign chamber is this little purple thing here. Right, so it's bounded by these 3 lines between vertices of the polygon. But the problem is, as I move around, as I change my choice of Z, so as I drag around the vertices of my polygon, for example, if I drag Z1 over here, eventually the region specified by, being on a particular side of this line and this line and this line, it will be empty because there just won't be any points in this polygon satisfying those conditions. So that's a bit troublesome. However, for every W chamber, you can find some Z so that the W chamber is non-empty. So there are no W chambers which are empty for all Z. And kind of that fact together with these things, that's what gives you the tiling results at the end. Okay, and very quickly, in 1 minute, just some more things that we're interested in, or kind of some more natural questions that come out of this. The first one is, so we have this correspondence between tilings, but from the hypersimplex side, at least, maybe you don't want to think about tilings, you want to think about something like regular subdivisions. So one question is, what happens to this correspondence between the hypersimplex and the amplituhedron if you add or remove conditions on the decompositions you're looking at. Another very natural question is kind of how nice is the nicest tiling? The dream maybe, or like if it's as nice as possible, you would hope that it actually gives rise to a cell decomposition of the amplituhedron. So that's another question which we're thinking about. And then the last question, maybe of most interest to physics, is what happens for other m? So throughout this whole story, I've been focusing on m equals 2, but the physically relevant case is actually m equals 4. So yeah, that's another question, is how much of our results or techniques would possibly extend to other m. All right, and thanks so much for listening.
Thank you very much, Melissa, for a very nice talk. So if there are any questions, feel free to ask now.
Hi, Melissa. Sorry.
Hi.
Thank you for your talk. It was very interesting. Yeah, I wanted to pick up the cluster variety part more. Why would you expect they're interesting, or how if they arise in your setting from these decompositions? But what do you expect from them? Is there any interpretation, anything particular that would be worth studying?
Yeah. So one thing that's interesting is that so one thing that's interesting is it shows that the amplituhedron decomposes into a union of positive parts of cluster varieties. So that's quite interesting. And another thing is that you have like many choices of which positive parts to pick, because the amplituhedron has many different tilings. So you can kind of look at lots of different combinations of cluster varieties. And if you look at their positive parts, you'll get the amplituhedron. So that's one pretty interesting thing. Another thing that's interesting is, so the amplituhedron lives inside of GRKK plus 2, but you can map it into GR2n. So it'll sit on some like linear hyperplane, a linear hypersurface in GR2n. I guess maybe you'll need to take into account like it'll live in some linear subvariety of GR2n once you map it over. And once you do that, okay, let me write some things down. So we've got a GRKK plus 2n, sorry, GRKK plus 2, it'll sit inside of GR2n. And the twister coordinates, Yij, I should be writing things into pullbacks, I'm just not going to. They'll turn into just normal Fluker coordinates, Pij. And so these cluster varieties, so they're not full dimensional inside of GR2n, but they're in there somewhere, and their cluster variables will be signed Fluker coordinates. So not positive, like it's not always just like Pij, it might be negative Pij sometimes. So you kind of have a mixture of positives and negatives. And so that's also pretty interesting. That's kind of like not studied at all. You know, usually we like to think about our cluster variables just being the Fluker coordinates, not with signs. And so yeah, it sort of suggests like maybe we should also be looking for cluster varieties whose positive parts are like more exotic matroid strata, something like that, not just like the positroid cells, but maybe something like a little bit stranger where you're specifying other signs of Fluker coordinates. Yeah, so those are the two things that I think are like the most interesting about these cluster varieties.
Cool, thank you so much.
Yeah. Okay, and someone like Xavier in the chat asks, what do you think extends to higher M? Yeah, so that's a really good question. I think so what we do not think extends to higher M is like an analogy between the hypersimplex and like the M equals 4 amplituhedron. We don't think that that's the right sort of thing to look at. Instead of the so if you're looking at something which has this kind of funny parallel to the M equals 4 amplituhedron, I think what you ought to do is look at a momentum amplituhedron for certain parameter values. In terms of the methods, I think we hope that our characterization of the generalized triangles for M equals 2 will be able to modify in some way, for the tiles for M equals 2, we'll be able to find some sort of nice characterization. for the tiles for m equals 4, maybe we won't be using these like nice subdivisions of the polygon, but maybe something more general. Yeah, I don't know if, I think Matteo and Lauren were in the audience. Well, Matteo's still here, Lauren was here before, so maybe they can say something about what they expect to extend. If they have any ideas.
Yeah, no, I think more or less, yeah, more or less, I think you covered. And the thing is, the T-duality itself, between these, the correspondence between cells and these tiles between these two objects somehow that you were mentioning, amplituhedron, moment amplituhedron, is expected to hold as a duality. But in terms of techniques, yes, there are more subtleties about considering twistor coordinates and other things, because of, yeah, you get something which is not, maybe you get polynomials in twistor coordinates that you have to consider. So there are slightly more nonlinear phenomenon happening, let's say. But it would be interesting also if the cluster algebra, the cluster structure would extend somehow cluster story.
Yeah, I should say maybe that we have some evidence that you could say, well, I guess we hope that you can say something similar about m equals 4, where the positroid tilings is actually a decomposition into positive parts of cluster varieties. And there's sort of some suggestions that might be true, but we don't have like anything very concrete to say about that.
Yes, exactly. So from physics, there were some cluster structures for m equals 4, but at the level of basically the facets of these tiles would correspond to sets of compatible cluster variables in a Grassmannian, 4, this time, not 2, and then we also extended this conjecture about other cluster variables which are compatible with sets, and they seem to have a certain definite sign. So there are some properties about signs of twistor coordinates and cluster variables that somehow seems to extend what Melissa was saying for m equals to 2, but we don't know what is the cluster variety to consider and how to define it. But it's very promising, I think, as conjectures, but more difficult since we are in Grassmannian 4, I think that's the major obstruction. Okay, yes. Are there more questions? Okay. Good. So, okay, then thank you, Melissa, again for the very nice talk. So looking forward to seeing you next week, and we will have Daniel Tismat from Hebrew University, and Michael Simkin will organize the session. So I will pass the thing to him next time. Thank you very much again, and see you soon. Bye.